So anytime we're finding arc length or surface area, we know that we need a derivative. So that's where we're going to start. We'll take the derivative before we do anything else. So let's go ahead and do that derivative first. 4/3 times 3/4 is 1. We subtract 1, we get x to the 1/3. 2/3 times 3/8. The 3's are going to cancel, and the 2/8 will reduce to a 1/4. And we're subtracting 1 from 2/3, subtracting 1, so we get negative 1/3. So there's our derivative. And then we know that when we're finding arc length, not only do we need the derivative, we're going to need the derivative squared. When we plop it into that square root formula, we have 1 plus y prime squared. So here's where we want to be a little careful. So I'm going to treat this like an A and a B. And I don't know if this is a sneaky perfect square trinomial yet or not. We'll know real soon. So difference of squares, when you square, we're going to get a squared minus 2ab plus b squared. Difference of squares. So we're going to have, and I'm not going to simplify it at all. So there's a squared minus 2 times a times b plus b squared. And b does not include the minus, so we're going to write it as 1/4 x blah, 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 to that squared. So there it is written as a perfect square, a squared minus 2ab plus b squared. All we want to do is simplify the middle term at first. So we're going to leave the first term and the third term unsimplified. And if that middle term simplifies to negative 1/2, then it's a perfect square trinomial. And it does. X to the 1/3 times x to the minus 1/3 is x to the 0, which is 1. 2 divided by 4. So we get negative 1/2. So that is our indicator that we do, in fact, have one of those sneaky perfect squares right there, because we have this half. So in the background magic, we know that a minus b squared is a squared minus 2ab plus b squared. And we know that a plus b squared, it looks identical except that the middle term is positive. So if you're focusing on the right-hand side here, and this right-hand side changes only in terms of the sign of the middle term, you know you still have a perfect square trinomial. So if you started with a perfect square trinomial and the middle term changes just by sign, you still have a perfect square trinomial. So now let's go in and take a look at, let's do it separately here before we even write it inside the integral, square root. So we know that our formula has 1 plus y prime squared. So let's add the 1 right here. So we're going to add 1 to y prime squared. And if we add 1 to y prime squared, the only thing that changes is that that middle term becomes plus 1/2. So now we know this is a perfect square trinomial by construction. We took a minus b and squared it, so we got this trinomial. It has to be a perfect square trinomial by construction. So we're up here. We added the 1. That changed the middle term sign and nothing else. So that means we're still dealing with a perfect square trinomial. And this will factor into a plus b quantity squared. So it's going to look a lot like where it came from. So there is our perfect square trinomial. And that's going to work out nicely now because in the arc length formula, we're going to have the square root of a square. So arc length, S, is the integral, I think we said 1 to 27 or something. 1 to 27. And we do square root of 1 plus y prime squared. So we're just doing the square root of this square. And so we're going to end up with that. So there's our arc length formula. Everyone tracking that okay? Still all good. Where the heck did it go wrong then? So, yeah, it's got to be, right? There's nothing left but algebra. Okay, so then the squares, the square and the square root go away. So we get that. And then we're going to integrate term by term. So we have x to the, we add 1, we get 4/3. Divided by 4/3 means multiply by 3/4. And then for the second term, we're going to add 1 to the exponent. So we add 3/3. We're going to end up with x to the 2/3. Dividing by 2/3 means multiplying by 3/2. So we're going to get 3/8. And that should still be positive, though. So we added 1, got 2/3. Divide this by 2/3, which means multiply it by 3/2, which will give us 3/8. And that goes from 1 to 27. Now we just have to plug in things and evaluate properly. So this is going to be 3/4 multiplied by 27 to the 4/3. Take the cubed root of 27 and get a 3. 3 raised to the 4th power is 81. So we're going to have that. Similarly here, cubed root of 27 is 3. Square it and get 9. And then we subtract off antiderivative evaluated at the lower end point. So we're going to subtract off 3/4 and subtract off 3/8. All good?
I think I screwed up somewhere in the multiplication.
And then we just put this into our calculator and get whatever the fraction is. Any step there you're unsure about? All right, yeah, so there's an arc length one. Tricky arc length. Tricky arc length. Any others from? That was 3 on chapter 6 quiz. All right, my brain is starting to work. All right, so let's go to some review questions. Let's see. We got to get out of this section, get over to this section. There we go. All right, so test will be chapter 6 and 7. Those are all the topics that will show up, or could show up. Maybe not every single one. So let's go ahead and just make note, no graphing calculators. You can't have one of those Casios that has the integration button. Right? So make sure you don't have the integral button. It's not fair. Your neighbor can integrate and check their work and you can't. Yeah, that one has an integral button. Yeah, that you can't. Yeah, so you can't use a calculator with an integral button.
Does this have an integral button?
Any graphing calculator has an integral button. That one, this looks like.
I mean, I don't know how to get there, so I did.
I don't see the integral without my glasses. Is this one integral?
This one is not work properly.
Yeah, this one does not have the integral button.
This one
That one's
have,
fine.
but this one is like not working properly. This one is not getting.
Well, it'll give you your answer. You can type in any integral and it will give you the answer. So you can check any integral you want with that calculator.
I was seeing like an integral button here. And
Yeah.
I tried graph, it's broken.
Yeah, you have an integral button though right
This
there.
one
Really?
is
Where?
not.
Yeah, you have an integral button.
Where?
But this one.
I'll
is
show you
not
later.
working
Let's keep going. I don't have time to talk about every calculator. So if you have it, you can't bring a calculator with an integral button. I will bring a bunch of those types of calculators. So not that thing. That. That thing.
Bring those ones.
Those things. No note card, no phones, all that stuff. Okay, so let's get started on the review questions. You should also note that these review questions come from MyMathLab. And you should see in MyMathLab, oh, I don't have it open right now. Maybe I'll open it later.
There's an exam review in MyMathLab.
Exactly.
Yeah.
Yeah, I don't have it open right now. But you see that, right?
Yeah.
So that's where these questions are coming from. These are from the exam review. So you can do it in MyMathLab as many times as you want, whatever works for you. So let's go ahead and we'll go through. I doubt we'll be able to get through all of these, so we'll get through as many as we can. So the first one is dealing with motion along a straight line. Should we do this, or does that feel like you understand it? So we have two of these right here. If we look at the titles I have on them, it might help us decide whether we want to do a problem or not. So this is also very similar. So we're gonna integrate in both cases to get to where we want to go. So maybe we should do one of these. Should we do the first one or the second one?
Both of them will be on the exam though, right?
One of them will. There's not going to be two of these, I don't think. I haven't totally finished it yet. Okay, so let's suppose we have the rate of change right there. So we've got the cells, there's the rate of change. We want to know what the future population is going to be in 15 days. So first we're going to find the general population, so the predictor. We're going to create a function that predicts the population in the future. So the key is that the population in the future will be the initial population. So we need to know where the population is starting to know what the population is at any given point in the future. Right? If you start with 2 rabbits, that's totally different than starting with 100 rabbits if you look 2 months down the road. So we need to know what the initial population is. And then we're going to add the change in the population. And the change in the population is the integral of the derivative. And if we're going to use the letter t to represent the time, then we often switch the letter on the inside so that we have a dummy variable that doesn't conflict with the variable in the problem given as t. All right. So the initial population is 200. So we've got 200 going in for the n sub 0. And then we're going to integrate from 0 to t. This function, the derivative function, the only difference is that we are going to replace that x, that t with an x. So that there's no conflict between the limit of integration and the dummy variable. So this is the integral of an exponential. And when we integrate an exponential, what do we do? To integrate an exponential, what's the first thing that we always do if we integrate an exponential?
It's the same. Divide by the exponent.
Yep, so keep it the same. The integral of an exponential is itself. That's the first part. And then the second part is the chain, well, we would call it the reverse chain rule. And so we divide by the derivative of the exponent. And so we get that. And then put in our limits of integration. And so then if we plug in the limits of integration, the upper limit of integration, all we're doing is changing the x to a t. And we have 0.21972. So that's the upper limit of integration. And now we have to be a little careful. A lot of times when we have a 0 in one of the limits of integration, we end up with the antiderivative being 0. But that's not the case here. When we plug in the 0, we're going to still have some math, right? Plugging in 0, the exponent becomes 0. E to the 0 is 1. So we're going to subtract off 50 over 0.21972. So we have that. And then we would just want to simplify that a little bit. We would add the two constants together. So we would add those two constants. So do whatever you would do in your calculator at this stage. And if there's any rounding, remember that we never round unless asked to round. So in a case like this, when we see this answer here, we're going to have to do some rounding. So on a problem like this, I will tell you what to round to. So whatever the question says to do, just do it. And I don't think, did it say in here what to round to? So on the test, it will tell you what to round to. And on something like this, because that went to 5 decimal places, I would probably say round it to 5 decimal places. So the final answer, the only thing we're really going to do is combine those constants. It's totally fine to leave this one as it is if we're going to round to 5 decimals anyway. So we would end up with that. So there is our function of t. This is our population at a future t value. And then it says, what's the population 14 days later? So what do we do to get that? Plug in 14. So then we're just going to replace all of the t's, well, the only t, with 14. Type it into your calculator, round it to 5 decimal places if that's what the instructions say. It'll tell you what to round to. And that's it. Plug that into your calculator, and that 14 is going to go right in there for t. All right, let's take a look at the next group. So these are what the worksheet was all about. And in looking at the worksheets, those problems on the worksheet, you really should be able to do each and every one of those instantaneously. Those are sort of the basic foundations for understanding integration used as a tool to find volumes and areas. So if you don't have those concepts down, make sure you start working on it hard right after class, because those are super key ideas. Let's see. So we only have one area problem here, so let's go ahead and do that one. It's usually helpful to draw a picture. Having a picture generally is the move. So let's go ahead and draw, let's see, where, I guess I'm going to draw tab, shapes. So let's go ahead and draw a picture of this. I thought I hit that. Okay, the first function is an absolute value function. And where is the vertex of that absolute value function? Where is the vertex? So an absolute value function, it's got a little point, call it the vertex. Where is that? 12, 0. Right? This is a shift to the right by 12. X minus a shift. Horizontal shifts are always opposite of what you see. We see a negative 12, that's a shift to the right. So that's going to be over here at 12. And this thing, it's a perfect V, 45 degrees each side. X over 2 goes through the origin, and that's just a line, right, with slope 1/2. Let's just draw a sketch. We don't have to get super precise. What we're seeing here is that there are 2 points of intersection there and there. So this is one of those unfortunate shapes that we have to use 2 integrals to find the area of. And we have to break this one apart. So we're going to separate this one right at 12, right there, right down the middle. And we're going to find the area to the left, right there, and the area to the right. So we're going to have to use 2 separate integrals. There's no way to do this one in one integral. We can't integrate with respect to y. I mean, we could, but we'd still have to use 2 separate integrals. So we'll just leave it with respect to x. We need to find the equations of all these things. So this one we have. This one is y equals x over 2. What is the equation of this right-hand line? Where x is greater than or equal to 12. What's the equation of that line? So no absolute value though, right? Because the absolute value takes care of both sides. So for to the right of 12, the absolute value is automatically positive. Right? If you plug in 13, 14, 15, it's already positive, so you don't need the absolute value signs. If you're to plug in numbers to the left of 12, what's inside is negative. And to make it positive, we multiply it by minus 1. So the equation of this line over here is y equals negative x plus 12. We multiply what's inside by negative 1. That's what makes it positive. So now we know what we're dealing with. We are going to have a vertical element for each of these little regions. So first we'll do the yellow one. So the yellow one will be an integral from, let's see, we don't know the limits yet. We'll check in a minute. But the upper curve, so we've got our element, upper curves on top of it, lower curves down below. The height of that element, or the distance between the 2 curves, is the upper curve minus the lower curve. So the upper curve is x over 2. The lower curve is negative x plus 12. So we're going to do upper minus lower dx. Limits of integration, we know the upper limit of integration is 12. We have to figure out the lower limit of integration. So that lower limit of integration, so at this point right here, we'll have to find both those x values. We're going to set this curve equal to x over 2. Right? Because this line right here has that equation. So we're going to set negative x plus 12 equal to x divided by 2. Multiply both sides, or do whatever we want to do. We could add x to both sides. So if we add 2 over 2, we're going to get 2x over 2. So we're going to get 3x over 2. And so x will equal like 8. So this x value right here is 8. So that's going to be our lower limit of integration. And then we're going to add the integral from 12 to whatever the right endpoint is. We can figure that out too. So here we're going to set x minus 12 equal to x over 2. So x minus 12 equals x over 2. Same type of thing. Here I'll subtract half x to the left, and that's going to give an x over 2. Add 12 to the right, and we're going to see that x has to be equal to 24. So x is 24. So that's going to be this x value far to the right. Good grief. 24. So that'll be the upper limit here. And what will the two curves be on the inside? So over here, upper minus lower.
X minus 12 minus x.
So now, isn't x over 2 the upper curve?
Oh, yeah.
Right, so that line, so if we look at it, this line right here is the upper curve. So it's x over 2 minus x negative 12 dx. So there is our setup. And then we just integrate, add it, and we're good. All right, any part of that you're not sure about? Ever going to see why we have to use two integrals? It's not vertically or horizontally simple. Austin?
Is there a reason why it's negative x plus 2 instead of negative x plus 12?
12.
Right over here? Is that where you're looking? Yeah, that should be a 12. Thank you. Yeah, this is the upper curve. The lower curve is negative x plus 12. So that should be a 12. Thank you. Whew. Good catch. All right, let's see next. So volume by slicing. So this is a super important question here. There will be these on the test. So general slicing to find the volume of the solid. So the solid whose base is a triangle with those given vertices. So let's go ahead and draw something in quadrant 1. What the heck? What are you doing? Click. So vertices are 0, 0. 2, 0, and 0, 2. So here is the base of our solid object. So that's the base. So the base flat on the ground. So there's the base. The cross sections perpendicular to the base. Yes, of course they're perpendicular to the base. That doesn't give us any extra information yet. The part that's important is right here. So when we think about our perpendicular, whatever the shapes are going to be, right? They're like this, they're perpendicular to the base, but we need to know how are they oriented. Are they parallel to y and perpendicular to x, or are they perpendicular to y and parallel to x? So here they say they're parallel to the y-axis. So if we draw a random element at an x, that satisfies that condition. Those are parallel to the y-axis. So that is our element. Now we know we're integrating with respect to x. As soon as we draw that element, we know dx is where we're going. Now it says that now we have to look at the shape. So let's call that h right there. If we were dealing with a square, the area would be h squared. If we were dealing with a rectangle that was twice as tall as the base, we'd be dealing with 2h times h for the area, 2h squared. If we're dealing with a triangle, we find the area of the triangle, whatever it is. Now they're telling us that the shape's going to be a semicircle. So this semicircle is coming straight out of the board at us. So let's come over here and draw that semicircle. So semicircle is coming out of the board. We're just going to take it and rotate it. So there's the semicircle. H is going all the way across here. Right? H is going from that edge all the way to that edge. So H is the diameter. Now we want the area. The area of that semicircle, the area is 1/2 the base times the height. No, that's not the area of a rectangle.
That's for triangles.
That's for some other shape. some other shape. What's the area of a semicircle?
1/2 pi r squared.
So 1/2 pi r squared for a semicircle. Thank you. 1/2 pi r squared. Half the base times the height. Wrong shape. What's the radius here? H divided by 2. Exactly. H over 2 squared. So the radius is only going halfway across. There's the radius, and that's also going to be this direction too. Oh, it is half the base times the height. Times pi. Okay, so if we simplify that a little bit, we can't do much, but we can at least write this as 1/8 times pi, and I put it, oh my gosh, my brain is not, I just had a big lunch. Gotta be careful here. So, oh no, it is h over 2. H over 2. Yeah, h is the whole thing, so the radius is half of it. So that's going to be 1/8 pi h squared. Okay, there we go. All right. Now, what is h? Well, h is the function that is that diagonal line, right? H is this diagonal line right here. That diagonal line gives us the value of h each step of the way. We know we need to rewrite this. This has to be in terms of what letter? What letter are we targeting? X. Because we're going to have a dx. Right? We have a vertical element which slides across an x interval, so we have a dx coming. So we want to replace that with x's. So when we look over here, we see that h is going to equal, let's write it with y's and x's first though. Look, what is the equation of this line? Y equals
-x plus 2.
-x plus 2. And so this tells us then that h is -x plus 2. That's the height. So we come over here and we're going to replace it with -x plus 2. So the area will be 1/8 times pi -x plus 2 quantity squared. So that is the area of the semicircle at x. How do we get to volume? Integrate it. So we'll just integrate that. And the 1/8 pi can, of course, come right out to the front. Or right as pi over 8. And then we would square this out. So we'd have x squared minus 4x plus 4. And we will integrate x's on the interval from what to what?
0 to 2.
Yeah, 0 to 2. So we're looking on the x-axis. We're looking down here. So that interval goes 0 to 2. Yeah, so h is the distance all the way across. H is the diameter. Everyone following? So let's do another one where the cross sections are disks. So if we have disks, it's going to be very similar to the one we just did. So if we draw a random vertical element at x, when we do this rotation around the x-axis, all right, the function that we're looking at, this y equals e to the negative 2x, that is the radius, that is going to be the radius. That function is going to be measuring the distance from the axis of rotation. So here, when that rotates around, we're going to get a disk that has a radius of r, and that radius is going to end up being just the function. So we're going to have y equals, or excuse me, a equals area of the disk. Area of the disk is pi r squared. Once again, we say to ourselves vertical element, so we're going to have a dx. That means integration with respect to x. That means the h has to get replaced, or that r has to get replaced with x's. So this is going to be pi multiplied by the function squared. So there's pi r squared. And when we have a power raised to a power, you multiply the exponents, so we're going to have pi e to the negative 4x. So that is the area of the disk at x. You can always check your extremities to make sure that your formula makes sense. If we looked at the leftmost extremity right there, that height is 1. And so that disk that it creates is a circle of radius 1. So the area is pi 1 squared. And if we come over here, the x value that we're pointing to is x equals 0. And e to the 0 is 1, so yeah, we get pi. So it's matching. So we have the right area function. And then volume, where are we going to integrate? From what to what? 0 to natural log 4, because we're starting at the left and we're moving from the left to the right through the x interval 0 to natural log of 4. So 0 to ln 4. So 0 to ln 4. We're going to integrate this. Let's go ahead and do this integral. This is not just a power rule. So the antiderivative of an exponential is itself. And then divide by negative 4. The derivative of the exponent is minus 4. This is called reverse chain rule, so then we're going to divide by that, and we will go from 0 to natural log of 4. I'll factor out the constant, minus pi fourths, pull it to the front, so that I'm only, for the antiderivative, I'm just going to imagine plugging into this exponential part right there. Keep it a little easier. When we plug in 0, we'll get e to the 0, which is 1. When we plug in natural log of 4, I have e to the minus 4, plugging in natural log of 4, minus e to the 0 is 1. So we end up with that. There's a little more simplification we can do here. How do we simplify that e to the negative 4 natural log of 4?
So e to the negative 4th.
So 4e to the natural log of 4 to the negative 4. That negative 4 comes up as an exponent, and then the e and the ln collapse. So we're going to have 4 to the negative 4 minus 1. 4 to the negative 4, we can keep going. You can plug into your calculator at this stage or whatever. 4 to the negative 4, so in the denominator, we're going to have 256. So we're going to have 1 over 256 minus 1, etc. Common denominator, simplify it. All right, any question on any step there? All right, so let's keep going then.
I have a question.
Yeah.
Regarding the pi. Is it best to leave the pi constant in before you do your integration, like till the very last second, or?
You can pull it. It's totally up to you. You can pull it out in the beginning. You can pull it out after.
Okay.
But we'll leave it there. We're not going to turn it into 3.14 or anything. We'll just leave it there the whole way through.
Okay.
And you can. We know that a constant inside factors right out to the front, so you can factor it right out.
Right. It just made it, I'm assuming, easier. Let's just pull that whole.
Yeah, pull that constant out. It's almost always easier to pull the constants out. Almost always. Other questions on it? All right, let's do a washer then. So here we have a function that is kind of curved, square root function. And we have a line, and they intersect and create this region. We're going to rotate it around the x-axis. if that little turquoise line is rotated around the x-axis, it creates a washer. And we have to identify the inner and outer radius. So the distance from there to there is going to be the inner radius, and the distance from there to there is going to be the outer radius. So the inner radius is from the axis of revolution to the first curve. The outer radius is from the axis of revolution to the further curve. So we're dealing with this type of object here, an annulus, and we want to find the area of it. So we have the inner radius and the outer radius. There's the inner radius, there's the outer radius. So the idea is that we're going to take the outer area and subtract off the inner area, and that's going to give us the area of the annulus. Yeah?
This might be a better question, but how can we tell if we need to use the washer method or the disk method?
If there's a gap,
If there's a gap.
you're going to have a washer.
Okay.
Because when that rotates around, if there's a gap between your element and the axis, if there's that space right there, that's what creates the hole in the washer. You're going to end up with a disk if the element is touching the axis that you're rotating around. If you're touching the axis that you're rotating around, there's no hole, there's no gap, so you get a disk and not a washer. So that's typically how you know. And then the area here is pi times the outer radius squared minus the inner radius squared. So that's the area of a washer. Big disk minus small disk. So what is the outer radius in this case? 32 root x, everyone agree? It's the distance from the axis of rotation all the way to the outer curve. There's the outer curve, so 32 root x. And then we have to square it, so 32 root x quantity squared minus the inner radius, just 8x, that's the first function that we come to, and that has to be squared. So that is our setup. Well, I guess we haven't set the integral up, but we're almost there for the integral. So the integral, the pi can factor to the front. We're going to integrate. We're going to square these things. So 32 squared times x minus 64x squared. And if we want the limits of integration, we're going to set these curves equal to each other. So 32 times the square root of x is equal to 8x. We can divide out the 8. Let's simplify it as much as we can. What do we do to solve a square root equation? Square both sides. So if we square the left side, we get 16x. If we square the right side, we get x squared. Nonlinear equation. Nonlinear means pull everything to one side and factor. And when we factor it, we will find our zeros. So we factor out the x. That tells us that the limits of integration are going to be 0 and 16.
Can't you just divide it by x?
Can't divide by a variable. Dividing by a variable, unless the variable is restricted, you don't know that it's not 0. So anytime you have a nonlinear equation, if you divide by a variable, you're going to lose solutions. So you always move everything to one side and factor. So nonlinear, move everything to one side and factor. So if you did divide out the x kind of willy-nilly, then you would only get one answer, x is 16. Right? Yeah, so whenever it's nonlinear, you want to go all to one side and factor. That's the strategy. And then our integration here is, we'll at least get to the antiderivative. So this is going to be 32. I didn't square 32 yet, but You know how to do that.
Is there a particular reason why when you write these out, you don't put the variable in the numerator, you have it to the side? I know mathematically it's the same thing.
Yeah, I mean, it's just usually, especially if the coefficient's a fraction, usually you pull it all to the front.
Okay.
If you're dealing with like just the denominator, it's not uncommon to write it like that, but yeah, it's just kind of your preference.
Okay.
It doesn't really matter. Doesn't really matter. I mean, a lot of times in the big picture, we like to be dealing with polynomials, and by definition, a polynomial is a constant times the power of x. And so if you put the denominator under the x, you're not writing it as a polynomial technically anymore.
Gotcha.
But it's still mathematically equivalent. So now we just plug in the 16 and simplify this, and we'll get our answer. Anything on there you're not sure about? Geometry is all of a sudden really important. Let's do a shell method, and then we'll do a random axis. And then if we have time, we can go back and do the other shell method. Let's see, so let's go ahead and do this one. We've got a picture for it, so let's go ahead and do it. So we've got this blue region, and we're going to do a rotation around the y-axis this time. So we're going around the y-axis. And we're told that we're going to use the, I guess all they tell us is the shell method. That's enough to know whether our element is vertical or horizontal. And will our element be vertical or horizontal here? So the y-axis is vertical. If we want to create a cylinder,
Our element needs to be horizontal.
our element needs to be vertical. Right? Visually look, right? If you're going to create a cylinder, they've got to be parallel to each other. If they're perpendicular to each other, you create either a disc or a washer if there's a gap. So if you want to create a cylinder, your axis of rotation and your element need to be parallel. Right? So that when you rotate around, you get a cylinder. So there is our random vertical element. We'll say that it's at a random x. Notice that when we create a cylinder, let's see if I can draw that cylinder in right there without totally messing up the look of this thing. So there's the cylinder that's created by our random element that we picked. We need to know two characteristics for this cylinder. We need its height and its radius. So the height is that distance right there, vertically. The radius is going across, right, from the axis of rotation over. That is the radius of that cylinder. So that's little r going across. We know that the area of a cylinder is 2 times pi times r times h. Circumference of the base, 2 pi r, multiplied by the height. So let's see. So, all right, so 2 pi. What is the radius here? Just x. It's the distance from the axis of rotation. Well, the distance to the axis of rotation for our element is exactly that x value. So 2 pi r, and then h is? H is the function?
Okay, h is the function.
H is the function. It's measuring the vertical distance. So because if we're looking here, this height is going from there to there, and that's what the function measures. The function measures the distance from the x-axis up to that curve. So that function measures that entire cylindrical height. All right, there we have it. So this tells us that the volume is going to be, we'll pull the constants out. We have 16 times pi integral, and we're going to have this be x over 1 plus 8x squared dx. they tell us the integral limits are 0 to 2. Well, hopefully you see that from the picture. Since this element is vertical, we are going in the x direction from 0 all the way over to 2. So there's an element sliding across from x equals 0 to x equals 2. For each of those x values, we have cylinders that are being created. What integration technique is needed for that? U sub. So 90% of the time when we do U sub, U is the exponent, U is the angle, U is the denominator, U is what's in the square root. Those are kind of the common things. So if we let U be 1 plus 8x squared, then du is 16x dx. 16x dx. Now that numerator, we can be a little clever here if we want. Right, this 16 out in front, that's just a constant. So we could say, oh, actually, let's imagine that constant sitting inside the integral. So then 16x dx, that's all going to be replaced with du. So 16x dx right there. There's a 16x dx right there. It's going to be replaced. So this is going to be pi integral. Now we changed to u, so let's not put those x limits there. And that's 16 gone, x gone, dx gone. That's all being replaced with du. I'll put it off to the side. And the only thing on the inside then is 1 over u.
And since we're going to eventually plug the function back in, we don't need to find the limits of integration for the u sub?
We don't. We can either leave and put little placeholders, totally fine, or this is simple enough we could convert. That's easy. If we plug in 0, we get 1. So it kind of depends on the complexity of this. If we plug in 2, we get 32 plus 1, which is 33. So the more complex that thing looks, the less likely it is a good idea to plug in numbers. But plugging in 0 and 2 are small enough that that's not going to be too weird. Antiderivative of 1 over u. So natural log of absolute value of u from 1 to 33. So we end up with pi times natural log of 33. Because we subtract off natural log of 1, and natural log of 1 is 0. All right, any part of that you're not sure about?
Did we drop the absolute value because we had already solved for the problem? Is that why we dropped it, or why?
So the absolute values here, when we plug in 33, the absolute value of 33 is 33.
Okay.
So because that's a positive number, we don't need the absolute value anymore.
So on the test, do you want us to show the u sub steps every time, or can we just kind of skip to that?
This is a great example of a problem that we could have done faster if you recognize that it was in log form. So here is the other way. If you are clever and you rewrote it like this. So if you left that, if you notice that, hey, this thing is close to being in log form, if you write it like that, now it's in log form. And if you want to use log form, that's totally fine. So just do this. Just put an LF over the equal sign so I know you know that it's in log form. And the integral in log form, the integral is the natural log of the absolute value of the denominator. So if you know that it's in log form, you can jump to the answer. It's natural log absolute denominator. These limits are still x limits from 0 to 2. So this would be pi times, plugging in 2 is, it's going to give natural log of 33, minus natural log of 1. And so we're going to end up with the same answer. And that's totally fine to use log form. Just do that so I know you know.
So for taking a point off, like if you forget dx one time throughout your like whole thing, and then like an integral, will you,
So on the first exam, I won't be quite as strict, you know. Normally, and I'll point out things that you really need to have on the subsequent exams, like the DXs. Normally, I would not take off one every single time there's a DX, but if you're notorious for not putting in the DX, I'll take 1 point off every 2 or 3 times. You know, kind of group it together. But leaving the DX off is like this. This is what a math teacher sees when you leave off the DX. You know, that's what we see. We see an empty square root. Square root of what? You know, like if you write the integral of x like that, it's like the integral with respect to what? That's what we see. This looks just as bad to us as that looks to us. It looks terrible. It's incomplete. You need to indicate what you're integrating. Like this is one symbol essentially. So you're chopping off half the symbol, right? It's like a vice. It's the integral with respect to x of what's inside.
Aren't we going to be doing weird stuff with manipulating DX?
Oh yeah.
Class 2.
Not in this class, but
Oh.
you will eventually. dx.
Isn't there a type of integration without a differential?
Not that I know of. There's a type of integral that's called a Lebesgue integral, which is an integral that doesn't have nice limits of it. Doesn't have like nice limits of integration. You integrate it in a different way. You don't do it with respect to x or with respect to y. But I've never seen an integral without a differential, though. Because the differential is part of the integral symbol. If you find one, send me a link, because I want to see that. But there is another type of integration called Lebesgue integration when you get into advanced calculus.
Back to that yellow step.
Yeah.
Did the 16 get canceled out because of that 16 value?
So the 16 got canceled out because 16 times x times dx is right here. 16 times x times dx. So the du is replacing all of that. So the du is 16x dx. So all of that got replaced with the du.
So you divided the 16 divided by that du.
So you have two choices. You can just sort of see that, oh, there's 16x dx, I'm going to do that. Or you could do what you're suggesting and rewrite this as x dx is du over 16, and then those 16s cancel. Yeah, you can think of it either of those two ways. But yeah, so yeah, we'll cancel. Okay, let's go ahead and take a 10-minute break, and then we'll do a little more. So. All right, let's do one more volume problem.
Math is getting confusing.
So one more volume problem. If we take y equals x squared, x equals 1, y equals 0, we're going to create a solid object when that's rotated around the line x equals -7. So let's go ahead and do that. So first, we're going to draw x squared and x equals 1. So here's x squared. Here is 1. And y equals 0 is the x-axis. So that's our region that's going to be rotated around our axis of rotation. Let's make our axis of rotation over here. So this axis of rotation is at -7. All right. So we're going to rotate all the way around there. We're going to create cylinders. So with cylinders, let's see, we've run out of colors. So we're going to draw a random element that's parallel to the axis of rotation, which means that element is vertical, which means dx. We're going to integrate with respect to x. So we need to know a couple of things. We need to know the distance to the axis of rotation. That distance to the axis of rotation, why aren't you turning it into a line? That distance is called the radius. So there's the radius. And then the height of the cylinder is over here. All right, so the area of a cylinder is 2 pi r(h). And what is the radius of the cylinder at x?
X plus 7.
X plus 7. Everyone see that? You can see it in pieces. The distance from this line over to the y-axis is 7. The distance over here is x, so it's x plus 7. Or you do right minus left. X minus 7 is x plus 7. The height is the function. Any questions on that setup there? So all we do is integrate that. And what are the limits of integration going to be? 0 to 1. So we're going to have this as our integrand. And limits of integration are given. So that's x equals 1 right there. That's x equals 0. 0 to 1. So random axis, if you draw a picture, it shouldn't be too hard, as long as you remember horizontal is right minus left and vertical is upper minus lower. All right, any questions on that? There's Aiden. Harrison is sick. Oh, Alex is missing too.
How many new lists have you printed since people have dropped?
Too many. Too many.
Because this class is looking suspiciously like half full.
Yeah, well, we have a few people sick today too.
It's that time of the year again.
I know. I know.
Actual statement.
Okay, let's see. We already did an arc length with a perfect square trinomial, so let's not do one like that again.
That looks okay.
This one is going to be. Let's just set this arc length one up, and we'll see if it turns into the trinomial or not. Looks very trinomial-ish, but let's at least just set it up. Anytime we see surface area or arc length, first thing we want to do is take a derivative. So we know we're going to need to differentiate here. So we're going to take x prime. So we're going to get 4y cubed. This one is 1/8 y to the negative 2. 1/8 y to the negative 2. So the derivative, the negative 2 is going to come down and give us negative 1/4 y to the negative 3. Negative 2 subtract 1.
Should just be white.
Yeah.
Should be just y cubed, right?
Oh yeah, the 4's cancel. Thank you. Yeah, 4's cancel. 4's cancel. 4y cubed, 4 cancels. Thank you. So there is the derivative. And if we do the derivative squared, here's where we don't get crazy. Just leave it as a squared minus 2 times a times b plus b squared. And here's where we'll notice if it's a trinomial or not. So a is to the left of the minus, b is to the right of the minus. And sure enough, this is going to be one of those perfect square trinomials. We already did one today, so we don't need to do another, but we'll at least write out this step. So the key is right here. Now we know that it's a perfect square trinomial because that's negative half. When you add the 1 to that, you're going to turn it into a positive half, and then it's going to factor into a plus b squared. The square root of the square will cancel, and you just have to integrate this with a plus in it instead of a minus. But we won't go all the way through that one since we already did one today. All right, let's get to surface area. So surface area, we have the ds part of surface area, which is just like arc length. But then out in front, we have a 2 pi r. And that changes everything. So we're going to take a look at this one where we have the line y equals 3x, kind of a steep line. And we're only going to look on the interval 3 to 7. So I'm just going to, we don't have to draw this to scale. But we're sort of dealing with this situation right there. So 3 to 7. This piece of the curve from here at 3 up to there at 7, that part is going to be rotated around the x-axis, creating a frustum of a cone. So that little red segment rotates around the x-axis. It's going to create a surface, and that surface is, frustum of a cone. All right. The formula for surface area, so if we have surface area, that's going to be the integral of 2 pi r ds. That's our generic formula. So if you think about one point going around, so we have one point there at a random x, so that one point at that random x rotates around and it creates a circumference. That's what the 2 pi r is. That's the circumference. And then ds is that minuscule tilted, whatever they call it, slant height. So you're thinking of tiny little frustums in here, and the ds is that tiny little slant height. All right, so then we pull out the 2 pi, and what is the radius?
3x.
The radius is the function, 3x. Radius is the function. So radius is the distance up to that red curve, so that's going to be 3 times x. And then ds, once again, is the square root of 1 plus the derivative squared. So we have y equals 3x. The derivative is just 3. So this is going to be 1 plus 9 inside there. And our limits of integration, we were told, are 7 and 3. So the surface area ones are usually easier than the arc length ones. All the constants out to the front, so we're going to have 6, square root of 10, pi. All that's out in front. The only thing that's left is x dx. That's all I see. And that's going to be 6 root 10 times pi. And then we do x squared divided by 2 from 3 to 7. Well, I guess we're going all the way on this one. So 3 root 10 pi 49 minus 9. Is that what you all see? 2 goes into the 6, 3 root 10 pi, 49 minus 9. So (120 root 10 pi). Surface area. Yeah.
Where does the 9 come from? Again?
That 9
Yeah.
is the derivative squared. So remember that ds is the square root of 1
1 plus
plus.
this. Okay.
Yep.
Thank you.
That's how we're going to rewrite ds. 1 plus derivative squared. All right, there's a surface area. Let's pass on that surface area for now, and let's get down to the springs. I want to do the springs, but I want to do the other things first. So let's go back to the spring. Let's make sure we have all the pumping things down. Those pumping problems are way easier than they seem at first, perhaps. As you start doing a few of them, it's like, oh, I don't want to miss this one.
On the prior exams, it focuses more on like chains and ropes than springs. Should we still make sure that we know?
You definitely want to know the springs. There's usually a spring problem. Maybe not always, but I would definitely know the spring. So let's go ahead and do, we'll get back to that spring, but let's do a work first. So the cylinder, if you see the cylinder on there as a work problem, hopefully you're like, yes, that's the easiest possible one, because every cross section has the same area. It's constant. You don't have to deal with the V or the trough, right? Every
So-
cross section has the same area.
The cylinder isn't bounded by a constraint function.
No.
Is it like a cone?
Cone is bounded on the left and the right with a function that's different all the way up. But here, we're not bounded by it. It's just constant, so we don't have to find like the left bound and the right bound. So that's what makes it easy. So when we take a random cross section, we are going to get that disk, and all we need to know is the radius of that disk. And then we have the area of the disk. And if we multiply it by dy, we get the volume of the slice. Okay, so we'll do our setup. So volume is going to be, not volume, work is going to be ADD area. Excuse me, ADD volume. ADD volume. That gives us work. ADD, acceleration density depth, or acceleration density distance, however you want to think about it. And just remember that this volume is not the volume of the tank, it's the volume of the slice right across there. It's the pi r squared multiplied by dy. It's that thin disk thing. It's a hockey puck. So here, acceleration, 9.8, using the metric system. Density of water is 1,000 kgs per meter cubed, so AD. And then that next D, think of it as distance to where you're pumping it out, or the depth from the top of the tank, or the depth from where you're pumping it out. What will that distance be? 9 minus y. So 9 takes you all the way. Y takes you just to there, so that little distance there is 9 minus y. So from here, so there to there is 9 minus y. So that's the distance it's pumped. Now, if the problem said we're going to have a pipe at the top that's 2 meters long and it's going to be pumped 2 meters above the tank and then out, then this distance would change. If there was a little pipe at the top that was 2 meters tall, this would be 11 minus y. Okay, so it would be a little further. But the limits of integration actually would not change. So there's ADD, acceleration, density, distance. Now volume. Volume is area multiplied by thickness. So the area is pi times the radius squared. So pi times 3 squared times the thickness of the slice. That is volume right there. That is volume. Those are the same. So you can see why this one's so simple, because there's no constants, or there's no variable other than the one. Everything's constant almost. So the limits of integration are what to what?
0 to 9.
So the tank is full, so we have water from 0 to 9. If they said the tank was only half full, we go 0 to 4.5. So the limits of integration reflect the physical location of the water. And so all these constants can come out to the front. So we end up with the 9800, we end up with the 9, we end up with the pi, and the only thing left inside the integral is 9 minus y dy. So, and you know how to integrate this. I'll write out one more step. So we'll integrate this to 9y minus y squared over 2, 0 to 9. Plug in the 0, plug in the 9. What are the units? Joules. Don't forget, on the exam, units. Any word problem, you need to have units. So we will have joules. So let's up the ante a little bit. Let's go to a conical tank. Conical tank is like one that's right in the middle. It's not the hardest, it's not the easiest. So let's do a conical tank. So there's our conical tank. Once again, we are finding work, and work is the integral of AdV volume. That acronym works fantastic for these. Super easy to remember, and as long as you remember that the volume is the volume of the slice, not the whole thing, it's pretty good, pretty good. So now we're going to look over here. We've got a random y value creates a cross-section. When we add thickness to the cross-section, that's going to create a slice. The radius is all we need in here. We need a pi times radius squared. This radius is variable, though. Depends on where we are. So we're going to have to figure it out. If we drew outside over here, and we think about our cone, if we just think about squashing it into quadrant 1, we're dealing with this type of thing. There's a 1. This is 8 up there, so this point is the origin, and this point is 1, 8. And that is how we're going to find its equation. We know those 2 points. What's the equation? Y equals 8x. We're going to solve for x because this radius is horizontal. So we want that distance right there. That's a horizontal distance. So for a horizontal distance, we want to isolate x. So there is that horizontal distance. All right, so now we're ready to plug everything in. So we have acceleration, density of water, depth, or distance that that slice travels. If we go right out the top of the tank, 8 minus y. And now we need volume. But again, it's not volume of the tank, it's volume of a slice, a representative slice. The volume of this representative slice is its area, which is pi times the radius squared. Well, the radius is y over 8. Right, that's the radius, y over 8. So pi r squared times dy. That is volume. Right there. That is volume. That is this volume right there. Volume of a slice. Limits of integration, 0 to 8. So more complicated than the other one, but we still have a fair number of constants here. So we're going to bring out that 9800. What else can we bring out? I guess the pi we can bring out. We can bring out a division by 64. And the only thing that's left inside, we have 8 minus y. So let me highlight what's left. 8 minus y and y squared. That's it. Everything else factored to the front. So that's going to be 8y squared minus y cubed dy. Integrate, blah, 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 and make sure that you have units, Newton meters or joules. All right, let's go to force. So let's go to the trapezoid, but for force, not for pumping. The trapezoid for pumping is a little more complicated than the trapezoid for force. Okay, so we have a figure at the right. It shows the dimensions of a small dam. Assume the water level is to the top of the dam. Find the total force on the face of the dam. We're finding force. Force, one dimension less than work. So this is ADD area. And by area, we mean not the area of the dam, but we mean the area of this representative strip right there. Caitlin?
Since we already did the trapezoid for a dam, will we do a problem for the trapezoid of a trough, or just?
Maybe. There's probably going to be a trapezoid,
Yeah.
one or the other. Just hopefully no semicircles, right? Yeah, definitely a trough is a good idea.
Are
I like
you-
that idea.
Are you writing the exam?
Yeah,
Okay.
I haven't finished it yet. Getting suggestions. You can beg me to put a semicircle on it. If you really want to challenge yourself, you would say, yes, semicircle.
You should make it a bonus question.
Bonus question.
Ah, for extra credit.
Bonus question is only available if you get all the other questions right. So ADD, any issues with this ADD? Random Y, here depth makes a little more sense instead of distance, but same idea, distance from the element to the top. ADD. That's pressure. Pressure is ADD. Acceleration, density, distance, that's pressure. Units will turn into pressure. Force per unit area, pressure. Area, now here's where most people screw up. It's not the area of the trapezoid, it's the area of this thin rectangular strip. So it's the width, we have to find the width of that strip, and then multiply it by its thickness, which is dy. So W times dy, that is the area that we are talking about. So that area is that. Okay, limits of integration, obvious, 0 to 3.
When we have these problems on the exam, will there be pictures included or just the work?
No, I'll put pictures for some of them, yeah.
Okay.
Yeah, definitely. How do we find W?
Right line minus the left line.
So, right minus left, yep. So we would have to find equations for these. One other option, instead of doing right minus left, we could draw a coordinate system, sort of, dead center, like that. And then we could find just half the way across, because if we find that right line across, we would just double it because of symmetry. So we could find this distance. So this distance here is going to end up being W divided by 2. So if we double it, that would give us W. So let's do that. Let's come out. Let's draw a coordinate system. So we'll focus just on the right half. So we've got this kind of setup here. That's going to be from 1 to 3. So it's going to look sort of like that. That's at 1. This height is at 3. So this point right there is 1, 0. This point right here, we come out to 4, so that's 2, 3. Everybody seeing that? If this total distance is 4, then half the distance is 2. So our top segment is 2 horizontally and then 3 vertically. Then we just have to find the equation of that line and solve for x. The equation of a line is y minus y1. Why not use the point with a 0? You could use this one if you wanted. Y minus y1 equals slope times x minus x1. So now we just need the slope. Well, the rise is 3 and the run is 1. So it's going to be 3x, or 3 times x minus 1. Do you see why it's 3? And then we isolate the x so that we're measuring horizontally instead of vertically. So if we want to measure horizontally, we need to isolate the x. So we get y plus 3 divided by 3. So now we have this distance right there. And we said that that is w divided by 2 if we go over to one edge from the center. So now we know what w is. W will be 2/3 y plus 3. So we're just going to double it. Double it. So we're going to have all this stuff that we can pull to the front. I'll just pull the 9800 to the front for the moment. So we have 3 minus y multiplied by 2/3 y plus 3 dy. Now we have our integral totally set up. So we're going to pull the constants out to the front. So we've got the 9800 multiplied by 2/3. And then on the inside, we're going to simplify by squaring, foiling this thing out. So we get minus y squared. We have minus 3y. We have plus 3y. Those cancel. And then plus 9.
We're doing symmetry, so we have multiple times 2.
We did right here.
Oh, that's where we put it. Okay.
That's what that 2 is right there. That 2 doubled. We took our x values measuring over to here, but we want the full distance across, so we doubled it right there. And then we have standard integration here. Y cubed over negative y cubed over 3 plus 9x, or 9y. Plug in the limits. Plug in the limits and you're good. All right, any question on the setup? Horizontal, right minus left.
9y, right?
Nope. When we FOIL this, first is 3y, last is minus 3y, so the y's cancel. And then when we do inner, we get y times negative y, which is negative y squared. And when we do last, we get positive 9. That makes sense? Everyone see that the y's cancel? Yeah, good question. Foiling. Let's go to our well, we have plenty of time here, so let's go to our spring now. Let's do the spring. And I think, let's see, that's just mass. Yeah, that's not mass. Let's do a spring. Okay, so we've got a shock, which is a spring, compressed 2 centimeters from equilibrium by a mass of 700 kg. How much work is required to compress the shock 4 centimeters from equilibrium? A mass of 700 kg exerts a force in newtons of 700 times gravity. Okay, so let's be careful with what we know here and what we don't know. For a spring, we know that force is equal to kx. So Hooke's law is what we use for a spring. It tells us the force as a function of displacement. And usually we are going to get our spring constant by knowing some data point. And if we look at this data point, what we know is that 700 g, that's going to be the force, 700 times gravity. So let's just write it as 700 times g, or let's put 9.8 just so you don't think it means grams or something. So 700 times 9.8. Everyone clear on that? So mass has no gravity included within it. So the force is going to be the mass times gravity.
Are you going to have us doing unit conversions like it was supposed to grams or something instead?
I am not so concerned with unit conversions. Yeah, no. So speaking of this, though, this brings up a point. Units of force in the metric system are newtons. What are units of force in the imperial system?
Slugs.
Good. Slugs. Slug.
Like,
This is why we use the metric system. Who wants to play with slugs?
is it like a slug,
Right?
like
Unless you're going to University of, California in Santa Cruz.
is it like a gun? Like a slug? Like a
No,
gun, like those-
the unit is just a slug.
That's what it's called.
That's what it's called. The units are slugs,
Okay.
like the mascot for the Santa Cruz folks, the banana
Slug
slug.
terror.
Okay, so yeah, so that's what one of those. Most of the times in physics, you're in the metric system, so you never come across slugs. But most people don't know that. All right, so force is going to be measured in newtons. So there we go, 700 g, where g is gravity. We don't know the spring constant, and we were told that it's compressed 2 centimeters. So we want to be careful here. We are going to have to do a conversion here because this is in meters, this is in centimeters. So 2 centimeters is how many meters? 0.02. All right, 100 centimeters per meter. So that we have to just make sure the units are lined up. So this tells us then that we have K equals 700 times 9.8 divided by 0.02. And if we wanted to, we could easily just move the decimal over if we don't have a calculator and we're just trying to get rid of the decimals really quickly. We could just do this type of thing and then write that as 700 multiplied by 490. Eventually we're going to need our calculator probably. Okay. So that is our spring constant. Spring constant is unique to the spring. It's kind of a, it gives you a measure of how hard it is to compress it. Now the question was how much work is required to compress it 4 centimeters from equilibrium. So the work, we're going to go from equilibrium to 4 centimeters. So 4 centimeters, if we write that in terms of meters, 0.04. And then our spring constant, which at this point I'm just writing as 700 times 490 times x. So that is our integral. For a spring, F equals kx. Pretty amazing that it's linear. Makes it easy to integrate. Marinus?
Should the 0.04 be negative since we're compressing it?
Good question. So we saw that it doesn't really matter. If you compress or stretch, you're going to do the same work. Now, if we technically are matching exactly what they have in the problem, then yeah, we should put a minus. But it's not going to matter. Everyone clear on that? That whether you compress or stretch, same work done. Work's positive. And it's going to be the same work here because as soon as we do this integration, we end up with an x squared over 2. So it's not going to matter whether we plug in positive or negative 0.04 because we square it.
But in theory, it's negative.
Yeah, if we want the integral to match reality, which is a good thing, then we should put a negative. Yeah. So then we're just going to plug and chug, get whatever we get. What are the units here? Joules. Yeah, so whatever we get when we type all that stuff in, those will be our joules.
Hyperbolic.
All right, let's do the hypers. So, derivative, we have a whole lot going on here. For many people, it's going to be helpful to do this kind of thing, where you take that power of 4. It is the outer power. That's what has to happen first. When we do derivatives, we always start on the outside. And it's not as obvious when you use this shorthand trig notation. So if you want to write it like that, that's going to be maybe easier to see. And then our derivative, power rule first. So the power comes down. We subtract 1 from the exponent. And I'm going to write it in the shorthand notation now. So that's the first step.
And double chain.
Double chain. So 4 comes down, subtract 1. Now we have to differentiate the base. Derivative of sinh is cosh 2x, all multiplied by 2. So when all is said and done here, we end up with negative 8 sinh cubed of 2x multiplied by cosh of 2x. And as you've seen a lot now, they are very loose about these parentheses. You don't have to wrap the hyperbolic angle up. Doesn't matter. Usually from the context, you can tell what they mean. Austin?
Will you accept if it was negative 4 times 2 cosh 2x right there?
You mean if you didn't simplify?
Like fully?
It depends on my mood. Depends on whether I grade your test first or last. It's best to always simplify. On the first test, I won't be as picky, but yeah, you should always simplify. Square roots, pull out the perfect squares. Fractions, reduce them. Just the basic simplification. Basic simplification. Okay, derivative of this thing. We've got double thing going on here as well. So if you need to write down the derivatives off on the side, do it. And if it helps you to do your trig ones first, so we know that if we have cosecant of x and we take the derivative of cosecant, we get negative cotangent squared. Is that what you said? Is that what you said?
I said the wrong one.
I said the wrong one too.
So is that right? Is that right or is that wrong?
I don't think that's right.
I don't think it's right either.
Oh.
That doesn't look right to me. So if there's any confusion, do this.
Negative cosecant x cotangent. So I was right.
If there's any confusion, start from the beginning and do this. And get all the way down. Yeah, did you say, Daniel, you did say it right?
I did say it right.
Good job.
I was questioning reality.
Yeah. There was someone else that said something different that was equally as... Minus cosecant? Is that right?
Yeah.
We all agree?
Yes.
What about the derivative of cotangent?
Negative cosecant cotangent.
No.
Cosecant squared.
Negative cosecant squared.
I know my trick.
Sorry, I didn't see
Good.
that.
What's that?
Sorry, I thought you said what was.
Oh, something else. Okay.
Cosine.
Okay, whatever you need to write down, don't just, if you're not 100% sure, write down some things on the side to make sure you're correct. Okay, so the one thing with the hyperbolics, the 3 primaries are positive, the 3 others are negative. The primaries are cosh, sinh, and tanh. So this one's definitely going to stay negative. So the first thing we're going to do is the derivative of a log is 1 over the inside. So we're going to take the entire inside, put it in the denominator, times the derivative of the inside. So we're going to have a negative. We know that we're going to have a chain rule giving us an 11 out in front. And so we're going to model this and get a cosec cotang. So cosec times cotang 11x. And then a cosec cancels. So here's an example of simplification you should absolutely do. And so this is all going to turn into minus 11 cotang 11x. What's derivative of tangent? Secant squared. Okay, so let's go to another hyperbolic with an integral. What format is this one in? Log form? So if you recognize that it's in log form, you can just go cut right to the chase. It's in log form, so we're going to get the natural log, absolute value of the denominator, plus c, minus 1, minus 1, minus 1, plus c. Do you need the absolute values here? No. Because the natural log, because the hyperbolic cosine is the hanging cable, and it's always positive. I wouldn't take off if you didn't take away the absolute value bars, though, because it's still correct.
What if we didn't have the parentheses? Can we just write natural log 19 plus cos x plus c?
Those you need,
Okay.
because there's a plus. If it was all multiplication, you wouldn't need them.
Okay.
Yeah, you always need them whenever there's an adding or subtracting. So log form. Okay.
This is the weird one.
Tanh squared.
That was on the quiz.
Tanh squared. So we need an identity. So, and if you need an identity on the exam for the hyperbolics, I'll give it to you. So I'll give it to you if you have one. So let's go look for a second. You don't have to know these. So if we look at our hyperbolics, let's see, where's tangent squared? Up here? No. Was it on that one?
Yeah, it was there. It's on the right.
Oh, right there. So 1 minus tan squared equals sec squared. So it looks similar to the Pythagorean. If you had to come up with it all by yourself, this is the one you'd have to know. If you knew, what do you do to this one to get the second one? Well, how do you, same way you would do it in trig. What would you do to get from one to the other? Hint, you divide by something. Divide by cosh squared. So if you divide everything by cosh squared, so if you divide by cosh squared there, you get 1. If you divide that by cosh squared, sinh over cosh is tanh, so you get tanh squared. 1 over cosh is sec, and so 1 over cosh squared is sec squared. So if you needed it, you should be able to get it from the original, from the primary one.
If we need an identity, you'll give it to us on the exam, right?
Yeah. Yes. I will give it to you. So 1 minus tanh squared is equal to sec squared. So 1 minus tanh squared equals sec squared. So tanh squared is 1 minus sech squared. Now we're golden. Because we already have these things like derivative of tanh is what? Derivative of tanh, sech squared, positive or negative? Positive. Sinh, cosh, tanh, all positive. So this is going to be positive sech squared. Primary 3, sinh, cosh, tanh. Like sine, cosine, tangent are the primary 3 for trig. So derivative of tangent is secant squared, so derivative of tanh, sech squared. So that means the integral of sech squared is tanh. So if we integrate here, we're going to get x minus tanh of x plus c. All right. Hyperbolic integral. So to integrate tanh, the easiest thing to do, just like to integrate tangent, the easiest thing to do is to turn it into sinh and coshes. So this is going to be sinh of x divided by cosh of x dx. And what form is that in? Log form. So that's in log form right there. So if we just put a little LF there, that's log form. So the integral of that is going to be natural log of the absolute value of the denominator, valued from 1 to natural log of 10. So once again, cosh is always positive. We don't need the absolute value bars. So we're going to have cosh of natural log of 10 minus cosh of 0 cosh of 0 is 1. It's the hanging cable, right? The hanging cable goes right through 1. So that's going to be 1. And this one we did not talk about that. We talked about it loosely, but I wouldn't ask you to know it. So that's as far as we would go. But what we talked about was that cosh is the average of exponential growth and exponential decay. So this could actually be simplified more, right? If you turn your cosh into e to the x plus e to the minus x over 2, you could plug in natural log of 10 there and simplify it.
You get like natural log of like a fraction.
Yeah, exactly. Yeah, we'll just leave it as this. So we're not going into the exponential definitions. You'll do that in other classes.
I noticed on 7.3 when you have the integrals of hyperbolic functions, you specify the absolute value for cosh. Do we have to remember that?
Yes, because this can be negative. Sinh can be negative. So let's look at that one real quick. So if you're integrating cotangent, here we do the same type of thing. We're going to just rewrite it instead of, so this one is sinh over cosh, cotangent is just flipped. So it's cosh over sinh. It's in log form though, right? That's the one really nice thing about these is that you don't have to deal with minuses with these basic ones. So that's in log form. So this is natural log absolute sinh. But you have to leave the absolute values there because the hyperbolic sine looks a lot like the tangent function. And the hyperbolic sine can be negative. So it goes up positive, goes down negative. So because it can be negative, you have to leave the absolute values. Must stay. All right, let's do a hanging cable one. So let's see. Let's do a hanging cable. I find that white so bright. Let's suppose that we've got a cable being pulled up onto rough. So we've got some sort of winch, and we've got a cable that's hanging. Let's suppose that that cable is 70 meters. Question is, how much work to wind up the entire cable?
The density of the cable.
What about the cable?
What's the density of the cable?
So we're treating the cable as a one-dimensional object. So we're going to say that the density is a 1D density. So we're going to say the density, so we're going to say 2 kilograms per meter. So as soon as we see that the density is given in one dimension, then we know we're dealing with 1D density and not 3D density. So if we wanted the cross-section of cable to matter, then we would have to be given kilograms per meter cubed. And then we would have to know the diameter of the rope and all that stuff.
Which we're not doing.
Not doing.
Okay.
No, so we're thinking of a cable or a hanging rope as just one-dimensional. So our work formula is the integral of ADD. Normally it's times volume, but this is for 3D, and we are going to change it to ADD length when we go to 1D. So we're taking away 2 dimensions of length. Volume is going down to just length, so we took away 2 dimensions of meters, if you will.
So now we just have dy.
So now that's just dy. So our ADD, we're going to have integral, we're going to have the 9.8. So there's acceleration. Acceleration, density, distance. Density is just 2. It's not 1,000 anymore because we're not dealing with water, we're dealing with a cable. So there's our density.
Distance is 70.
Nope.
70 minus y.
Yes. So if we pick a random cross-section of chain that's at a height of y, then 70 minus y is the distance that link has to travel. And then length, again, is boiled all the way down to just the thickness of that cross-section of cable, just the thickness of that thickness is dy. And then we're going to integrate from 0 to, we're going to do it all the way up, we're going to go from 0 to 70. So that'll be the integral that takes us, that fully winds it all the way up. And we can, of course, bring some of these things outside. Maybe I'll just leave the 2 there because we're going to divide by 2 in a minute when we integrate. At least, well, maybe not. We'll see. So that's what we would end up with. Okay. What if we only wanted to wind up half this cable? What are we going to do?
0 to 35.
So if we want to only integrate, if we only want to wind it up halfway, we have a couple of choices. So your strategy, is that going to turn into a circle? Well. So let's suppose we've got this 70-meter cable, and we want to wind it just halfway. So we're going to wind it so that it ends up being like that. So 35 goes up, 35 doesn't. So Austin said integrate from 0 to 35. So, and then anything else, or is that enough?
Should be no difference.
So if we go 0 to 35, cross section, so let's see, so ADD, so A is the same, D is the same. What's the distance going to be?
It would be 70 minus.
70 minus y still. That still doesn't change. And that's it. That'll do halfway. So that's the quantum way. That's that terminal state way where if we integrate from 0 to 35, we're actually thinking of these links as the ones that are being moved up onto the spool. If we integrate from 0 to 35. If we integrated from 35 to 70, because those are the actual links being rolled up, then we would also have to include the lifting of the bottom half of the cable with an MGH. Okay?
Would you be able to like take 0 to 70 and then just divide the whole equation by
No.
No, that's not. Okay.
Because if you think about the links near the winch, it's less work to lift the links closer to the winch up than to lift the links near the bottom. So it's not going to be symmetric. Lifting up the top half, lifting up the bottom half will be totally different.
My math will ask you that exact question.
Unless the rope is
Okay,
horizontal.
So you have to.
Unless we're winding horizontally.
Does the same logic apply if you wanted to only wind up like a fourth of it versus
Then you have enough
it's just that number divided by 4?
Yeah, exactly. Yeah, that's the whole.
That would be,
All right, any other ones? Any questions from the worksheet or any of the homework or quizzes? All right, study hard. I'm so psyched to get to grade tests this weekend.
Are you?
I am psyched though, like with a small class, it's like, this class, we used to have a cap of 36 on all these calc classes. I used to teach for over 15 years. Every time I taught Calc 2, there's 36 students. That's a lot of tests.
except minus the people who
26
dropped.
is great. It's like, I don't mind grading at all when there's only 20.
Or you could make your SI do it.
Yeah, exactly.
SIs can't grade tests though, sadly.
They
No.
can't?
No,
Yeah.
because they're not, that's a TA role, they're not TA.
True.
Truth. Truth.